Hi, welcome to Sunil Maths tutorial, functional analysis class number 27. In this video, we learn a theorem and one problem. Let us see the statement of the theorem. A non-empty set capital X of a normed linear space capital N is bounded, implies and implied by f of x is a bounded set of numbers for each f in conjugate space n star. So let us see the proof. Let capital N be a normed linear space and capital X is a non-empty subset of N. Capital X is a non-empty subset of N. That is, capital X is subset to N and this X is not equals to pi, non-empty set. So we have to prove that capital X is bounded, implies and implied by f of x is a bounded set of numbers. F of x is a bounded set of numbers for each f in the conjugate space n star. So part 1, suppose assume that f is bounded. Suppose capital X is bounded. Suppose capital X is bounded subset of n. By the definition of bounded subset, there exists a positive constant. K1 such that norm x is less than or equals to K1 for all x belongs to capital X. Let it be equation number 1. This is nothing but the definition of bounded subset. Suppose capital X is a bounded set, then there exists a positive constant K1 satisfying the condition norm x less than or equals to 1 for all the elements x belongs to capital X. Let it be equation number 1. Now we can show that f of x is bounded. Since f belongs to n star, it implies f is a functional. Conjugate means it is a functional space. So f is a functional. F is a functional means every functional is bounded. Therefore f is bounded. F is bounded means there exists another constant K2 such that mod f of x is less than or equals to K2 into norm x for all x belongs to capital X. Let it be equation number 2. This is also from the definition of functional. Now from equation 1 and 2 we conclude that. You see, let it equation 1 and equation 2. So from these two equations, from equation 1 and equation 2, we conclude that mod f of x less than or equals to K1 into K2 for all x belongs to capital X. Suppose this K1 into K2 treated as some constant r, where mod f of x less than small r for all x belongs to capital K, for all x belongs to capital X. In both the places, for all x belongs to capital X. For all x belongs to capital X in both the places. This condition implies f of capital X is bounded set of numbers for each f belongs to the functional n star, conjugate space n star. That's it. This is the first part of our theorem. Let us see what we take and what we prove that. Suppose that capital X is bounded set. I write the bounded set definition here. F of norm x less than or equals to k1 for all x belongs to capital X. Let us, since f belongs to n star, so f is a functional. Every functional is bounded. So again, by the definition of boundedness, there exists another constant k2 satisfying this condition, mod f of x less than or equals to k2 into norm x. Now combining these two, equation 1 and equation 2, we can write mod f of x less than or equals to k1 into k2. Suppose this k1 into k2, the product k1 into k2 is equals to some constant r, then we say that now mod f of x is less than or equals to small r for all x belongs to capital X. This shows us f of x is bounded set of numbers for each functional f belongs to n star. So now we prove the converse part, reverse part, converse. Let us assume that f of x is bounded set of numbers. Let us assume that f of x is bounded set of numbers. F of x is bounded set of numbers. Now we can prove that this f of this capital X is bounded. Capital X is bounded. For our convenience, we exhibit the vectors in capital X by simply writing capital X is equals to set of all elements small xi. Consider the natural embedding. That maps from small xi into capital Fxi of capital X into the conjugate space n star. That is Fxi can be defined as Fxi of small f is equals to f of small xi. So by applying this definition, you can write like this: f of capital X is equals to f of xi, small xi, such that each small xi belongs to capital X, which is equals to fxi of f such that each xi belongs to capital X. For each f belongs to conjugate space n star, for each f belongs to conjugate space n star, the function or the set f of x is bounded. The set f of x is bounded. This shows us what is this f of x? Collection of fxi of f. Collection of fxi of f is bounded set for each f belongs to n star. Already we know that this conjugate space is complete. N star is complete. It follows from uniform boundedness theorem. It follows from uniform boundedness theorem. The collection fxi of f is bounded subset of n star. It is clearly bounded subset of n star. So this condition implies as norm fxi is bounded. Fxi is bounded. If norm fxi is bounded, then the collection norm fxi such that each xi belongs to capital N is bounded set of numbers. So So you observe that here each xi belongs to capital N. By natural embedding, we know that natural embedding preserves natural embedding preserves norm properties. Natural embedding preserves the norm properties. This condition implies as norm fxi is equals to norm xi for all xi belongs to capital X. So if you apply this condition here, the collection norm xi such that xi belongs to capital X, which is subset to capital N, is a bounded set of numbers. Is a bounded set of numbers. This is nothing but this set is nothing but f of capital X is bounded set of numbers for each f belongs to the conjugate space n star. So which is required one? Capital X is a bounded set of numbers. Capital X is a bounded set of numbers. So here this is not f of x, this is not f of x. I mean collection xi means this is the collection of all norms norm xi such that xi belongs to capital X is bounded set of numbers for each f belongs to n star. This shows us capital X is bounded set only, not bounded set of numbers. It is only a bounded set. That's it. This completes the proof. Therefore, we prove that capital X is bounded if and only if f of x is a bounded set of numbers. That's it. Here in this video we prove one problem also, and one of the simple one. Let us see. Let capital B be a Banach space, and N be a normed linear space. If sequence Tn is a sequence in the collection script B of B, N, such that T of x is equals to limit Tn of x. Exists for each x in capital B. Then prove that capital T is a continuous linear transformation. This is our problem. So they given that capital B be a Banach space, capital B be a Banach space, and capital N be a normed linear space, and Tn be a sequence, in script B of B, N, the set of all functionals defined from B to N. And it is defined in a way such that T of x is equals to limit Tn of x. For all x belongs to the Banach space capital B. Our aim is to show that we have to prove that this Tn or this T, both this T, this T is continuous linear transformation. So first we prove that it is linear. To prove that capital T is linear, this is the first side heading. Let us take two vectors. Let x comma y belongs to B, and alpha comma beta are any scalars, and x comma y belongs to the Banach space. Now consider T of alpha x plus beta y, which is equals to limit Tn of alpha x plus beta y. Limit Tn of alpha x plus beta y. Limit n tends to infinity you can take. This can be split. Limit n tends to infinity Tn of alpha x, Tn of alpha x plus limit n tends to infinity Tn of beta y. Again, these alpha and beta are scalars, so they cannot influenced by the limit alpha into limit n tends to infinity Tn of x plus beta into limit n tends to infinity Tn of y. Again, by the definition, you can write like this: alpha T of x plus beta T of y. In the LHS we have T of alpha x plus beta y. In the RHS we have alpha T of x plus beta T of y. Therefore, we prove that T of alpha x plus beta y is equals to alpha into T of x plus beta into T of y for all x comma y belongs to capital B and alpha comma beta are scalars. They belongs to the field capital R. This condition shows us capital T is a linear transformation. Capital T is a linear transformation. Next, you have to show that this capital T is continuous. This linear transformation is continuous. So by definition we have T of x is equals to limit n tends to infinity Tn of x for all x belongs to capital B. So you observe that this sequence, since Tn of x is continuous, which implies Tn of x is bounded. Every continuous function is bounded. So Tn of x is continuous, so implies as Tn of x is bounded. So by uniform boundedness theorem, by applying uniform boundedness theorem, we have norm Tn of x is also bounded. This is the point. So Tn of x is continuous, obviously it is bounded. By applying uniform boundedness theorem, norm Tn of x is also bounded. Now, what is norm Tn of x? Norm Tn of x is nothing but, so are taking limit on both sides. Limit n tends to infinity, norm Tn of x is equals to norm T of x. So this condition implies us norm Tn of x limit n tends to infinity norm Tn of x is also bounded, in another way I can explain like this. So consider this. Here norm Tn of x is also bounded, implies limit n tends to infinity norm Tn of x is also bounded. This is the point. This is right way. Also bounded. What is this limit? This limit is equivalent to norm T of x. So implies as norm T of x is also bounded because of T of x is equals to limit Tn of x. So norm T of x is equals to limit norm Tn of x. So you can conclude like this, limit, which implies norm T of x is also bounded. If norm T of x is bounded, then we conclude norm T of x is less than or equals to a, where small a is any constant for all x belongs to capital B. This condition shows us capital T is bounded. It means it is a bounded linear transformation. Every bounded linear transformation is continuous. Therefore, capital T is continuous. This is the second point. Capital T is continuous. Hence, finally, we conclude that capital T is linear. Linear transformation as well as it is it is continuous also. This completes the solution of this problem. In the next video, we solve one more theorem. Keep learning. Wish you all the best.